Welcome everyone. In today's lecture, we are going to look at a new topic, which is fatigue. Again, in this lecture, we are going to just have a very basic introduction of fatigue. You will look at fatigue in a lot more detail when you do your design class, which is MAE 342 or MEE 342. Okay. So this is supposed to be just a very basic introduction. So we will just cover the basic concept of fatigue and a few terms that are important in fatigue, and we will look at what is called as an SN diagram. Okay. So essentially, by the end of this lecture, you will be prepared to do three things. You'll first of all understand the concept of fatigue loading of structures, which is something that we haven't looked at in this class so far. You'll be able to define various terms related to fatigue, such as fatigue strength and endurance limit and so on. And finally, you will be able to understand the relationship between fatigue strength and the number of cycles to failure. Okay. So what is fatigue? Okay. Fatigue is essentially progressive and localized structural damage that occurs when a structure or a material is subjected to repeated cyclic loading or repeated loading. So what do I mean by that? So if you think of, say, a tensile test, right? So essentially you have a specimen and then you apply a force P and you progressively increase this force P until the material fails. Okay, that is a typical tensile test. And then from the tensile test, you can get the stress and the strain and things like yield strength and ultimate strength and so on. In a fatigue loading or in fatigue, in the case of fatigue, this load is not constant or monotonically increasing with respect to time, but rather it is cycling or it is changing with respect to time in a particular manner. Okay, so if you think of, say, a beam like this, okay? So if you apply a bending moment like that, right? Essentially you will have compression in this part and tension in that part, okay? So but then the points where you have compression and tension are essentially going to stay same with respect to time. On the other hand, if you take this exact same beam, but instead of applying a force or a moment M like this, say you apply a moment like that and then change the moment in the opposite direction so that it goes like that, okay? Then what happens? This particular point which is under the compression is now going to become under tensile stress. And this particular point which is under tensile stress is going to come into compression. Okay? Now, if you look at the stress at any one point here, okay, and then you look at it as a function of time, what you will see is that the stress at that point, sigma, and if you look at it as a function of time, it can change something like this, like that. Okay, this is corresponding to the case where M is like this, and this is corresponding to the state where M is like that. Okay, so essentially the nature of stress or the direction of the stress or the sign of stress, whichever way you want to look at it, is changing with respect to time. Okay, so this need not be the only case. You can have cases where the stress is smoothly varying with respect to time. Okay, and that is what happens in a lot of cases. So if you look at the stress at a specific point in the structure, it might change like this. Okay, this is sigma and this is T. Okay, and the stress might change something like this, and so on. Okay, so initially it's, say, under tension, then it goes to compression, and it again comes back to tension and goes to compression and so on. Okay, so this kind of a loading is what is called as a fatigue loading. Okay, now why are we worried about this fatigue loading? Okay, the reason that we are worried about fatigue loading is that when you have this kind of a cyclic loading, then failure will start at stresses that are much lower than your yield strength or the ultimate tensile strength. Okay, so if you take a bar of steel, for example, and then apply or do a tensile test, you will see, okay, it yields at maybe like 300 MPa and it fails at like 400 MPa. Now, if you take the same steel bar, but now you apply fatigue loading or cyclic loading, then what you will see is that you don't need to go to 300 MPa to cause plastic deformation or 400 MPa to actually fail the material completely. You might be able to break this material by just applying a load of 250 MPa. Okay, so that is the important point of being fatigue. So when you have fatigue or cyclic loading, the materials or structures fail at much lower stresses than your yield stress or ultimate strength. So why does this happen? The reason that fatigue causes failure at lower stresses is because when you have a cyclic load, especially if it's above a particular threshold, then you have microscopic cracks that usually form. Okay? And these cracks usually form on the surface of the material or surface of the structure. Okay? And then once these cracks form, as you keep loading the structure again cyclically, these cracks start to propagate. So essentially they become longer and longer. And eventually at some point they become long enough that they cause an abrupt or a catastrophic failure. Okay, that is how things fail by fatigue. And you might think that why is this important? It is important because if you look at engineering structures, almost 90% of the failures that you see in service are due to fatigue. Okay, so fatigue is a very, very important part of failure analysis that you have to take into account. Okay, and the reason that we have to worry about stress concentrations is because often these fatigue cracks start at stress concentrations. So essentially when you try to design a material or design a structure, you try to reduce the stress concentrations as much as possible because these are the points where this fatigue crack starts. Okay? So what is an example of fatigue loading? Okay? A simple example that you can think of is essentially the axle of a car. Okay? So say this is your, say the front axle. Okay? And then you have your tires. Okay? Okay? And these are your tires. Okay? And the weight of the car is applied, say, at 2 points here. And assume that it is, equally distributed. So essentially you have a force P here and a force P here. Okay? So because of these two forces, you're going to have a bending load. Okay? And if you draw the bending moment diagram for something like this, it might look something like this. It is going to be constant between the two forces and it's going to be like that. So that is going to be a bending moment. Okay? I may not be very particular about the sign here, but the magnitude is kind of going to look like that. Okay? Now, this is a bending load, but your tires are rotating, right? So what is going to happen? So if you look at, say, a cross-section here, okay, and then look at the cross-section in the side view. So this particular point, for example, might be under maximum tension, or in this case, maximum compression. Okay. Now, as the tire starts to rotate, this point is essentially going to start rotating because that is the shaft. So essentially it's going like this, and then at some point it's going to come over here. Okay? Now the load is still acting in the vertical direction. So if this point on the cross section was initially under the maximum compression, now when it comes over here, it is going to be under the maximum tension. Okay? And in between, some point here, some point here, and some point here, it is going to be less compression. And here it's going to be zero stress. And here it's going to be tension, but lower than the maximum value, right? So essentially, every time your tire makes a full turn, this particular point in the shaft on, say, this cross-section essentially goes from maximum compression to zero stress to maximum tension and back again to maximum compression. Okay? So essentially, you have the bending stress at this point. Actually, for that matter, at any cross-section between these two forces P, if you look at the bending stress at any point on the circumference, the stress as a function of time is going to look like this. It's going to start maybe somewhere at the top. It's going to go down and then go up, go down and so on. Okay? So essentially, as the tire rotates, the shaft or the axle that connects the two tires is essentially going to have a fatigue deformation or a cyclic deformation where the state of the bending stress keeps changing from compression to tension and back to compression and so on, right? And of course, you can imagine how many times your tire is going to rotate when you take a trip. Maybe it's thousands of times. And then you're going to take thousands of trips. So it's going to be millions of cycles through which the shaft is being subjected to. Okay? So essentially you have loadings that are cyclic and they can easily stretch into hundreds of thousands of cycles, sometimes even millions of cycles. Okay? So this is an example of a fatigue loading of an axle of a car. Okay? It is same for the axle of a railroad car, for example. It is no different. But another case of fatigue loading that you can think of is essentially the wing of an aircraft. So each time the aircraft lands or takes off, you're going to have plenty of vibrations. So each time the wing is vibrating, what essentially undergoing is that essentially you have a cantilever beam that is essentially bent that way and that way. Okay, so if this is the wing of the aircraft, essentially you can think of it as a cantilever that is being bent or vibrated this way and that way. So what happens? If you look at a point somewhere on the top of the wing, it is again, the stress state there is going to go from compression to tension to compression to tension so many times, right? So essentially, almost everything that you look at in practice has some kind of fatigue loading, even though it may not be apparent. Okay? The fatigue loading might come because of vibrations in many cases. Sometimes it's because something is rotating. So irrespective of what the actual cause is, many engineering components are subjected to fatigue. And this is this fatigue loading that often leads to failure. Okay, so that is the reason why we need to worry about fatigue. Okay. Now, how do you characterize the properties of a structure or properties of a material with respect to fatigue or cyclic loading? Okay. For that, what we use is called as a rotating bending test or rotating beam test. Okay. So the setup here is actually very simple. You essentially have a simply supported beam that is subjected to two forces, okay, of equal magnitude split by a distance. So if you think of the total length of this beam as L, both of these forces is essentially at a distance A from the supports. Okay, so you have these two forces. Okay, so this would be just a static loading. But what you do in addition is that you rotate this beam about its axis even as you apply these two forces. So what essentially happens is that if you have a point somewhere here, that point is initially under compression, and then as you do a half turn, that point essentially comes from here to here, and then it goes to tension. Okay, and then if you do another half turn, it goes back to compression. So each time you rotate, as you keep these two forces constant, essentially the points on the surface go from tension to compression and back to tension, or vice versa. Okay, so essentially you have a fatigue loading. And then what you do is you apply a specific force P, and then you find out how many cycles of this rotation is required for you to actually break this shaft or break this beam. Okay, so essentially what you do is you specify a value of P, you apply a certain P, and then you rotate it as many times as is required and find out after how many cycles it breaks. Then what you do is you change the value of P and repeat the experiment. Okay, so essentially what you're doing is that you're going to get a plot where essentially you have P on one axis and the number of cycles it took to fail on the other axis. Now, you don't just use P, you essentially convert this force into the bending stress, sigma. And then you plot sigma versus n. So essentially this plot is going to look like this. So essentially you can think of, this is the sigma that you applied, and this is the number of cycles it took for it to fail. So typically what you'll see is that if you apply a large sigma, then the number of cycles it takes for it to fail is small. If you apply a smaller sigma, then the number of cycles it takes for it to fail, which is n, is going to be larger. Okay, so that is how you characterize the fatigue properties of a material. Okay, and the maximum stress or the stress that is required to cause failure for a given number of cycles is what is called as the fatigue strength of the material. So it is often denoted by the symbol SF. Okay, so you can think of the fatigue strength as that, okay, if I want to fail this material or if I want to fail the shaft in say 50,000 cycles, what is the stress that I have to apply to make it fail in 50,000 cycles? So that is the the fatigue strength corresponding to 50,000 cycles. Now, if you say, I want to actually make this shaft fail not in 50,000 cycles, but 200,000 cycles, then the stress that you have to apply for that particular number of cycles, that is the fatigue strength. Another way you can think of it is, if I want my shaft to at least survive 50,000 cycles, what is the maximum stress that I can apply? Okay? As long as you apply the stress below that value, below that SF value, then you're fine. If you go beyond that, it will fail. Or if you actually, if the stress that you apply becomes equal to that, there's also a good chance that it will fail. Okay? So this fatigue strength is not a single number, but it is actually something that depends on n. So the number of cycles to failure and the maximum strength or the maximum stress that you can apply to get that failure in that many cycles, they are related to each other. Okay? So that is how you construct what is called as a SN diagram. Okay? So this SN diagram, this S basically corresponds to the fatigue strength, SF, and N corresponds to the number of cycles to failure. Okay? And typically, if you make a plot between SF and N, so this is your fatigue strength, and this is the number of cycles to failure, what you see is that initially, the fatigue strength is more or less independent of N. Okay, so whether you cycle something for like 10 cycles or 20 cycles or 50 cycles, the amount of stress that you have to put in to actually make it fail is more or less constant. But then once N reaches a particular value, typically around 1000, then you start to see some kind of an inverse relationship between the fatigue strength and the number of cycles to failure. Okay, and that relationship kind of looks like this. It is kind of like that. Okay, and then typically what happens is that at some point of N, the fatigue strength becomes constant. Okay, so this is how an SN diagram typically looks like, and this is true for most steels. For certain other materials like aluminum, it is a little bit different, but we will not go into that here. Okay, so what does it essentially mean, right? If you want a material to survive a large number of cycles, then the stress that you have to apply has to be smaller. Okay, so if you want to say, go to say N equal to like 10 to the 5 cycles, for example. Okay, if you want the structure or this material to withstand 10 to the 5 cycles, then you want to make sure that the maximum stress that you apply on this material is below this value. Okay, it should be below that value that I have indicated here to make sure that the material does not fail due to fatigue into the 10 to the 5 cycles. Okay, so that is essentially the idea. Now, if you have a very small number of cycles, say usually around 10 to the 3 or smaller, then it doesn't matter what stress that you apply. Okay, as long as it is below this particular value, the material is unlikely to fail. Okay, similarly, if you go beyond a certain cycles, usually this is about 10 to the 6 cycles, right? Beyond 10 to the 6 cycles, it doesn't matter what stress you apply. Okay, so as long the stress that you apply is below this value, the material is not going to fail. Okay, or the other way you can think of it is, if you go beyond 10 to the 6 cycles, you have to apply at least this much stress, okay, for the material to fail. Okay, so this is how the SN diagram looks like, right? So essentially for low number of cycles less than 10 to the 3, the SF value is constant. For very large number of cycles, usually more than 10 to the 6 cycles, the value of SF is also constant. And that value is what is often called as the endurance limit. And it is often denoted by the symbol SE. Since similar to SY, which is for yield strength, you also have what is called as the endurance strength or endurance limit. Okay, as I told you, there is a relationship between SF and N, between 10 to the 3 and 10 to the 6 cycles. Okay, and that is usually captured by a log-log plot. So if you plot log of the stress that is required to cause failure versus a log of the number of cycles to failure, then it is often there is a linear relationship. Okay? So if you actually look at what these precise mathematical relationships are, so if you look at the fatigue strength, that essentially is approximately equal to 0.9 times SUT, where SUT is the ultimate strength, and this is true for n less than 10 to the 3. Okay, for less than 1000 cycles, the fatigue strength is approximately 0.9 times SUT. Now, if you look at the range between 10 to the 3 and 10 to the 6 cycles, then at that point, the relationship is slightly complicated. It turns out to be something like this. This is 0.9 SUT, the whole square, divided by SE, which is the endurance limit, times n to the minus 1 over 3 logarithm of 0.9 SUT divided by SE. Okay, and that is the relationship for 10 to the 3 less than n less than 10 to the 6. Okay, so essentially that is the fatigue strength for this particular cycles, this particular range of cycles. And for n greater than 0.10 to the 6, SF is basically equal to SE, okay, which is the endurance limit. Okay, and for many of the steels where the endurance limit applies, this SE is approximately equal to 0.5 times SUT. Okay, this is typically for steels. Okay, I just want to note that for some materials there is no endurance limit. So what that essentially means is that if you increase the number of cycles indefinitely, then the stress that you need to apply to make it fail keeps falling indefinitely. So for many alloys that are made of aluminum, for example, you don't have an endurance limit. So essentially, if you go to like 10 to the 7 cycles, the amount of stress that you have to apply is smaller than for 10 to the 6 cycles. If you go to 10 to the 8 cycles, the number of the stress that you can apply is going to be smaller than for 10 to the 7 cycles, okay, and so on and so forth. So this endurance limit is only applicable for certain materials, and it's typically true for steels. Okay. Now, I just want you to make sure that this relationship is clear to you, right? What we're essentially saying is that if I choose the number of cycles that my component has to survive, right, then I want to make sure that the maximum stress that I apply is less than SF. Okay, that is what the relationship essentially tells you. Okay, you tell me this component has to survive for 100,000 cycles. Okay, then I can tell you that the stress has to be less than 50 MPa so that it doesn't fail within the 100,000 cycle. So that 50 MPa is your fatigue strength. Okay, now you can also invert this relationship and write your N in terms of SF. Okay, so I want to remind you that this SF is essentially the stress required to cause fatigue failure. Okay, and that depends on the number of cycles in which you want to cause failure. You can invert this relationship and write N as a function of SF. And if you do that, the relationship for N, especially in this range, okay, turns out to be something like this. It is SF times SE divided by 0.9 SUT the whole square to the power of minus 3 divided by logarithm of 0.9 SUT over SE. Okay? So what this relationship tells you, again, this is true for 10 to the 3 less than n less than 10 to the 6. So you can think of this relationship as, okay, if I tell you what stress I'm going to apply, okay, this is a stress applied. Okay, if you know what stress you're going to apply, then you can predict that it is going to fail in that many number of cycles. Okay? In the first case, this particular relationship essentially tells you that if you specify the number of cycles, what is the stress that is required for it to fail, or what is the stress below which you have to be so that it doesn't fail. This relationship here essentially tells you that if you tell me this is the maximum stress I'm going to apply, this relationship tells you this number n is the number of cycles after which it is going to fail. Okay, so you can interpret it in both ways. Okay. Now, I told you that this relationship between log n and log sf is kind of a constant between 10 to the 3, or it is essentially linear between 10 to the 3 and 10 to the 6 cycles. So if you take log sf, logarithm of sf, and then plot it as the logarithm of n, you'll essentially get a plot that looks like this. It is going to be straight, then it is going to be linear, and then again it's going to be straight. So this region is about 10 to the 3 to about 10 to the 6. Okay? So essentially, for n less than 1000, the fatigue strength is essentially constant. Okay? And that fatigue strength is, as you know, 0.9 SUT. For n greater than 10 to the 6, the fatigue strength is again constant, and that, you know, is nothing but your endurance limit. Okay? But in between 10 to the 3 and 10 to the 6 cycles, the fatigue strength reduces linearly, or the log of the fatigue strength reduces linearly with the log of the number of cycles. Okay? One thing that I want to note here is that this relationship only hold good if your samples are flaw-free. Okay, so essentially, if these are pristine samples with no cracks or anything to start with, then these relationships hold good. If your sample is flawed, so for example, it has some porosity or it has some crack already on the surface, then the number of cycles to failure is going to be dramatically reduced. Okay, and the other thing that I want to notice that I wrote this, or I drew this very nice curve saying that, if you plot SF versus N or log SF versus log N, you essentially get this very nice straight line. But it is not really a really nice straight line. If you look at the actual values that you get from experiments, if you look at, say, 10 to the 5 cycles, okay, and then you look at 5 different samples, okay, what you'll see is that one sample essentially fails at this stress at 10 to the 5 cycles. The other sample fails at that stress at 10 to the 5 cycles. Another sample goes way beyond. Okay? So essentially, there is a lot of scatter in the fatigue data. Okay? So fatigue is a stochastic process, so you can't deterministically predict when something is going to fail. So if you apply the same stress on the same kind of specimen in 5 different experiments, in one case you might have the specimen fail in 15,000 cycles. In another one, it might fail in 14,200 cycles. In another one, it might fail in 16,000 cycles. So if you take the same material, the same nominally identical sample, and then you use the same boundary conditions, you apply the same load, you're going to have a variety of number of cycles where it's going to fail. Right? So essentially, fatigue is not a very precise phenomena, but all these diagrams give you is a sense of where you can expect things to fail. Right? So essentially, if you say, okay, like I'm going to apply a cyclic load of like 50 MPa, right? So then you can say, okay, this material is probably going to fail somewhere between 50,000 and 70,000 cycles. Okay? That's the amount of precision that you can get. Okay? So that's something that I want you to keep in mind, that this SN curves have a lot of scatter, and these are mostly experimentally determined. There's no theory or formula that you can use directly to obtain them. Many of them are just done empirically. Okay, so that was actually a very very basic and quick introduction to fatigue. So when you go to your design class, machine design class 342, then you will look at fatigue in a lot more detail and how to actually design for fatigue, how to take into fatigue in terms of extending the lifetimes and so on. Okay, thank you.